All right, let's review how to find the inverse of a function. This is a pretty important skill, and it's going to come up in calculus. We're sometimes going to be concerned about a function, and then sometimes we're going to want to do things with its inverse. So we'll have to find the inverse of the function as well. So when you go to find the inverse of a function, there's 4 steps. 3 of them are like trivially easy, and then one step, the third step, is somewhere between easy and impossible. Right? So it just depends on the function that you're trying to find the inverse of. They can be very simple. Some functions don't even have inverses, so it may not be possible to find the inverse if it doesn't exist. So let's look at one of the more difficult problems where the algebra comes up. Can be a little bit tricky. Let's work through that, and then most of the inverses that we run across in this class should be about like this problem or easier. They shouldn't really get too much harder than this. So let's take a look at things. So we want to find the inverse of this rational function, f of x equals 2x minus 1 over 3x plus 5. So step 1 is that we're going to replace our function notation f of x with y. So that's easy. You literally just rewrite things, but instead of writing f of x, you write y equals. Okay. Step 2 is that we're going to go through and we're going to replace all the x's and y's. We're going to swap all the x's and y's with each other. Okay. So in this case, if you look at the what we ended up with in step 1, all those y's have been changed to x's and all those x's have been changed to y. That's step 2. Pretty easy. Nothing really fancy going on right there. Okay. Step 3 is where, step 3 sometimes is a fairly straightforward step. Sometimes it's very, very difficult. Sometimes it's not even possible. We'll talk about that in a minute. But let's go ahead and see what step 3 would be, and we'll walk through the algebra. If you can do the algebra and follow along with the algebra we have to do to solve for y in this case, then you'll probably be okay with most of the problems that we do in here. Okay, so now what we're going to do in the next step is we're going to solve for y. And we have 2 issues that we run across in this problem when trying to solve for y. One problem is that there's 2 y's. So we've got 2 of them, and we have to figure out how to go through and get y equals, but we have 2 y's right here. That won't be too bad. The other difficulty that we run across is that one of those y's is in the denominator of the fraction. And once we take care of those 2 problems, we're pretty much in good shape. So the first step that we're going to do is we're going to multiply both sides of the equation by this denominator, 3y plus 5, because that solves one of our problems. If we're trying to solve for a variable that's in the denominator, we need to get it out of the denominator. So that's what we do here. We take that equation, we multiply both sides of the equation by 3y plus 5. So on the left, that gives us x times 3y plus 5 equals 2y minus 1. And then on the left, we distribute that x in, right? We're ultimately going to have to solve for y, so we need to get it out of those parentheses. So you distribute the x in, giving us 3xy plus 5x equals 2y minus 1. Okay. Now the issue is we have to get all the y's on one side of the equation and everything that doesn't have y's on the other side of the equation. So you can see what went on here. I subtracted 5x from both sides of the equation, and I subtracted 2 y's from both sides of the equation. So that gave me all my y terms on the left and all my non-y terms on the right. Okay. So we've taken care of that issue with y being in the denominator, but we still have the issue of there being 2 y's, and we're trying to solve for 1, y equals, right? Well, it's not too bad. All you have to do is factor that y out, right? So see how we've got this? We factor the y out of there, right? We factor it out in front. It becomes y times the quantity 3x minus 2 equals negative 5x minus 1. And now what we have is that single variable. So we've solved both of our difficulties now. One was that y is in the denominator. That's taken care of. One is that we had 2 y's. That's taken care of. We're down to a single y. So what you're going to do here, notice what's in this parentheses. You can do these problems where you end up with, some kind of complicated mess inside of these parentheses, but we don't care. As long as it doesn't involve a y, it's just some expression that's multiplying the variable that we're trying to solve for. So you just divide by whatever that quantity is. It's just like if you were trying to solve for 2y equals something. if you were trying to solve that for y, you would divide by 2. That's all we're doing here. We've got something that's multiplying our variable y, so we're going to divide both sides by that thing. When you do that, we get y equals negative 5x minus 1 over 3x minus 2, and we've now solved for y. That's that tricky step. So it wasn't too bad. We kind of see what's going on there, right? And then the fourth step, luckily, is a very easy step again. So our last step is really just about putting things in a convenient form. And we use this, it looks like an exponent of -1, but it's not. Do not treat this like an exponent. Do not try to apply exponent rules to this. That -1 that we see on the F is not an exponent. It's just the notation that we use for inverses. So when we say F inverse, with this negative, that's the -1 up there. This is read F inverse of x, so that's the inverse. We found the inverse of our original function f. F inverse of x is equal to negative 5x minus 1 over 3x minus 2. So we now have the inverse, which inverses can be very, very powerful depending on the type of problem that you're doing, right? Sometimes they're not important. Sometimes they hugely, hugely helpful to you. So how do we know that we didn't make a mistake there? Right? How do we know that there wasn't some error along the way? Well, you have a couple of choices depending on how important this is, right? So what you could do is you compose the function and its inverse. If you compose a function and its inverse, it should all simplify down to x. And then you do it the other direction. You compose the inverse and the original function, and it should simplify down to x. Now, in this case, that's going to be kind of a mess. It's going to be a bunch of algebra we probably don't want to have to deal with unless we really, really want to make sure we did this right, because we already have the function being a rational expression, and then when we compose it, we're going to have rational expressions inside of our rational expressions. So could be an issue. I mean, we can do it, but it's going to be a whole lot of work. Turns out there's a much easier way to check if something is an inverse or not, and that's by graphing it. So let's switch over to that. All right, so recall that a function and its inverse reflect across the line y equals x. So if you had the one function out there, so let's put our original function out there. If this was a piece of paper and we folded it along that line y equals x, this original function should line up right on top of its inverse. So that's one way to check, because our brains are pretty good at picking out symmetry pretty quickly. So your brain can immediately tell if something is wrong or not. In fact, when I originally worked through this problem and went to graph it, it was immediately obvious that I had made a mistake somewhere in my work, because the graphs were clearly not reflections of the other ones. So I knew, oh, looks like I have a typo somewhere, a small mistake, and then I went back and found it. So it's really helpful to, quick and easy way, throw these in a graphing utility, see if the symmetry looks right. If so, move on ahead. Okay, so if we look at the original version and its inverse, you can see that if this was a piece of paper and we folded it along y equals x, that purple lines, when we fold it, would end up right on the green ones. And so we see that symmetry and we go, yeah, looks like we got the inverse correct. So I can have a pretty good faithful belief that this function is correct, and I can move forward with it without having to go through all the algebra that would be involved in rigorously checking it. Now, if it's really, really important that you get it right, then it might be worth going through all that algebra. But just by graphing it, we can be pretty sure that this is correct, right? That we didn't make any kind of mistake here. So really helpful when we do that. So remember earlier I talked about not every function has an inverse. Well, you don't want to spend a bunch of time trying to find the inverse of a function if that function doesn't even have an inverse. So how do we easily check if something's even going to have an inverse or not? Well, we use the horizontal line test. So if you just pass a horizontal line over your function, if it only ever hits that graph in one place at a time, then that graph is 1-to-1 and it is invertible. That means it's worth trying to find the inverse because there will be one, right? So for instance, if we had something like a y equals x squared, this function is not invertible because it fails the horizontal line test, right? You could imagine if we took this function and did that reflection across the line y equals x, we'd get x equals y squared, right? So this is what the inverse would look like, except there's a problem here in that it's not a function. So this function here, this new purple one, would fail the vertical line test, meaning it isn't a function. And that's, if you think about it, that's where the horizontal line test comes from. It's basically predicting, yeah, when you go through and try to find the inverse, that inverse is going to fail the vertical line test, right? So it's just giving you a heads up. So if we take those out of there and we just look at our exponential function, we can see, for instance here, oh yeah, this exponential function passes the horizontal line test. Therefore, we know exponential functions have inverses.